Hi guys, welcome back to the HYSYS video. And yeah, in the last video we talked about adding the component list and some of the fluid packages. So we want to continue on that. So I'm just gonna use the last file. I'm gonna press save. However, the thing is that when I press save, you find that there are component errors for acid gas property package, and it says the component list for acid gas contains an unsupported amine combination, and it says select supported amines to replace with. I don't really have a clue what that means yet, but I'm just gonna write adjust components. I'm just gonna leave it as that and let the HYSYS kind of do its magic, whatever it is. Yeah, this one's not that sure, because basically if you have only one amine, that's not a problem, because then it'll just be these individual ones. But if you want to combine them together, then that's going to be an issue. So probably what HYSYS is saying is that maybe it's not been calibrated well to make predictions for combined amine, combined amines. So you can only do individual amines. So yeah, so this is, well, in this video we probably want to continue on our reactions. There's a lot of thunder outside. Okay, so as you can see in the reactions tab now, there are 3 sets of reactions. All of them are under acid gas. So these are basically, let's say you have these, all these are based on the carbon dioxide and the hydrogen carbonate reactions. Every single reaction that happens within the amine system is being recorded here. For example, you can see the HS minus here, CO2 SH minus. All these are actually reactions that describe the absorption of acid gases such as CO2 and H2S, etc., etc. So that's quite a comprehensive list. So you even have ammonium here, which is quite interesting. And of course here you have some other things also, like some carbamates. I think there's some ammonia that's attached to a carbamate, some carbon dioxide minus. I think that's a carbamate. But yeah, basically all these reaction sets you see here for the CO2 and H2S absorption. And now we want to add in, maybe we want to add in the methanol reaction for catalyst. So I'm just going to name these sets. Okay, they are just called set 1, set 2, and set 3. So we can't rename them, so let's just leave it as that. But this I want to rename to methanol synthesis. Okay, I'm going to press save, and there's nothing in there yet. This methanol synthesis, there's nothing inside, and I have the option of attaching it either to the Ping-Robinson NRTL or the ASME steam table. So obviously I'm just gonna let it go to the Ping-Robinson extended NRTL package. So I'm going to do that. So it should be added. Okay. So I'm just going to press save first. Okay, so it has been attached to the associated fluid package, which is the Ping-Robinson extended NRTL. So that's methanol synthesis. So yeah, you do need packages besides acid gas for simulating reactions, because acid gas only simulates the capture and separation of CO2, and of course, though it happens to predict very well the distillation of methanol. I mean, you can show that in another video. It cannot be attached to this methanol synthesis reaction. So how do we have a methanol synthesis reaction? Under this methanol synthesis reaction set, I'm going to press add reaction, and for us we're going to use this HYSYS as the reactant source. I'm going to put a heterogeneous catalytic. Now this is one of the most complicated reaction types under HYSYS. So heterogeneous catalytic, maybe you're gonna react methanol on some kind of solid catalyst, such as copper, zinc, and alumina, or some other kind of things you can find online like zinc and zirconium. So, okay, sorry, it's recording. ZrO2, ZnO. Yeah, so this is the one I was talking about, the zinc and zirconium one, but there isn't a, this is under a Creative Commons thing, so anyone can take a look at it. So you're just going to press view full text, and yeah, this is a very good catalyst, one of the very good ones, because it resists sintering, and you can see that the even at 320 degrees, well, yeah, just for reference, most of the conventional copper, zinc, and alumina, they operate about 280 and they start sintering there. But this one, it says that the catalyst shows excellent stability for more than 500 hours on stream, blah 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 blah. So it's very promising. But do we have, you know, do we have a catalyst model? Oh, that's the challenging thing. They characterize the catalyst, but there's no model. So much as we like to use this most advanced catalyst, we can't quite do it yet until there's a kinetic model available. So what do? Now just add the heterogeneous catalytic reaction first. I'm just going to rename it as methanol synthesis 1. Okay. Okay, so we'll come to this table, and we have a lot of stuff to add in, and I'm not going to quite show you all of how to add that in. Maybe I'll do it in another video. But what I'll do is I'll probably want to take a look at some of the previous reaction models. Okay, so these are some of my old, project files, and there was already a catalyst model there. That's not completely correct. In fact, it kind of underpredicts the catalyst activity by about 95 times. So it kind of shows a very deactivated kind of catalyst. That's what it is simulating. But we'll stick with that for now. I mean, just to show what the idea of these video series is, to show you what HYSYS can do and how you can play around with the stuff in HYSYS. The kinetic models, probably if there's time, I'll probably look at some other videos. But yeah, this is what we do. Okay, so we'll take a look at the reaction set. We're going to use this thing called SCSI-PEX model, and we're just going to copy and paste everything we see here. Okay, so you have this few components here, so you can copy into your HYSYS as well if you want to play around with it. So I have CO2, hydrogen, CO, methanol, and water. Okay, there's no need for CO here since the stoichiometric coefficient is 0, but you will see it is quite important because it's one of the competitive adsorption thingies. Yeah, if you know catalyst reaction, well, basically what CO is here for is that it competes for the active sites. If you're not sure, don't worry, just copy and paste. Perhaps you maybe another video, if there's a real need for that, we'll make and if there's a real need and there's time, then I'll go and record all those things. Okay, so for now we're just going to key in the numbers. Okay, so 5 things, right? CO2, CO, H2O. There should be hydrogen as well, and there should be water. Oh, the water is already added. What am I missing? Methanol, obviously. Okay, so that's part 1 done. So this is just the CO2 hydrogenation. Okay, so I'm going to rename it as that. I'm going to press save, and I'm going to press save very often because I don't want to lose data. Okay, so I'm just going to follow. CO2 is -1, hydrogen is -3, the rest is 1, and CO is 0. These are the stoichiometric coefficients, so we use 1 mole of CO2, so this is 0. H2O, we are making 1. Hydrogen, we are taking 3, and this is 1. Okay, So I'm just going to save. And so far that's alright. So we have done with the stoichiometric coefficients. And based on this, we're going to use partial pressure. And the base component is going to be CO2. Reaction phase is vapor. The maximum and minimum error is such. Minus 273.1, 3000. This is just a temperature range. Okay. So partial pressure. And we're going to use vapor phase. The reaction temperatures are as follows. And I'm going to change the base units to be about the same. Not going to explain too much in detail here. I'm just going to key in one catalyst model and yeah, just to run. The idea is wanting to give you. I want to give you some example of how you play around with the units in HYSYS. Yeah. So let's set it up first. So the base units are in atmospheres. The rate units are in gram mole per cm cube per second. So I'm just going to do that. Atmosphere. So in gram mole per cm cube per second. I'm going to save that. And here there are some reaction rates. And I'm just going to copy and paste everything here. So 2 point something, yeah, 2.8747 E minus 20. So I'm just going to press the copy button. Copy. I'm going to paste it here. Yep, and that's fine. So if you want, yeah, you just copy the values over. That's what I'm doing. So that's okay. I'm okay with negative energy values because we already did most of the calculations already. So what are these components here, and what is this numerator forward and backward? Well, basically you look at the kinetics help. Okay, you see Langmuir. Oh wait, I don't need. I can just use the HYSYS help file. Okay, let's go to F1. I'm gonna close this for the time being. Nope. F1. Heterogeneous. Yeah. So, okay, the usual thing in heterogeneous catalysis is that you have this Langmuir-Hinshelwood model. This is very common. So basically, what we have is that we have a numerator and a denominator. You see a numerator here and a denominator here, and then mostly, you know, the catalytic reactions will fall under one of these three categories, and basically there may be a forward term, maybe a reverse term, and it's gonna get pretty messy. So HYSYS has a standard way of, you know, keying in those reactants and products. Okay, it looks a bit complex. Yeah, so there is a standard way. If you look at the HYSYS file, okay, it's lagging on me. Okay, so this one's the one I was testing. Yeah, so kinetics help. Yeah. So let's say you have the forward reaction. So this part I'm pointing the arrow at is the forward, and this is the backward. And this, of course, is the denominator which you saw just now. So don't worry about all these basis things first. So this K, let's just go with the familiar stuff. The K in the front is the constant in the front. And then you will have some F basis, whatever that is. So let's take a look at, well, let's take a look at some examples, yeah. Just going to say Langmuir, Hinshelwood. Okay, this is not very helpful. Doesn't matter. Okay, never mind. Yeah, but the idea is basically this is the net forward rate, and this is the net backward rate. And you can see basically if you go to heterogeneous, yeah. So you see, when you go to your forward rate, you may have some K plus, Ka, Kb, all these equilibrium constants. You'll have to rewrite all these K plus, Ka, Kb. You have to combine it yourself manually into one term. Then this Ca and Cb will be the so-called basis they're asking for. So if you're going to use this example, right, of the Ka, Kb thingy. So the forward reaction rate will be K plus, Ka, Kb. Then you have to multiply the whole thing together, and it will be in some form of Arrhenius form, like so. So HYSYS gives you a lot of freedom to choose and specify. So this is the pre-exponential factor, the exponential minus e by RT. And so that's the K. And then there's this T to the power of some beta looking thing. I mean that some models actually use that, but if not, beta will be 0. Then you'll just be the A exponential minus e by RT. Yeah, and same goes for the backward rate, which is this K prime over here. So the net backward rate. So where does the backward rate come? So if you see this equation here, if there's a minus something, K minus, Ka, Kb, something like that, then that will be in the backward rate. That will be the backward rate, which is kind of absent here. So for this case, in this example, this K prime is just 0. This A is 0, everything is like 0, that kind of thing. And what is this F basis? F basis, like I said earlier, is this Ca Cb term. Can you see this Ca here and the Cb here in this first row? I'm highlighting this Langmuir-Hinch rule. Look at the numerator and look at the Ca and Cb. These are your bases. Okay, these are your bases. This is what it's talking about, the basis. So they look for the backward basis. Of course, that's nothing. Then in the denominator, you have 1 plus K1, F1, K2, F2. So F1 basis, F2 basis. So what is that all talking about? Well, you can look at the thing here. So you see in the denominator, you have a form like 1 plus KACA, KBCB, KPCP, all these kind of things. So no worries. They are also looking for 1 plus K1, F1, K2, F2. So again, the Ka and Ca, that will be the first term we want to key in. So K1 here will be the Ka previously mentioned, then F1 will be the Ca. Of course, the basis can be in partial pressures units, so it can be K1 PA, K2 PB, etc., etc. And so that's what the numerator and denominator is about. So why did I just spend the last few minutes explaining that to you? Well, you can see that over here there'll be some forward order and reverse order things. So what it's saying here is that the forward order will be this K then F basis. This is the F basis. So the CO2 will be, well, since we are using pressure units, so the F basis at the front will be PCO2. So let me use a notepad. K times F basis equals to K times PCO2. So you see this forward order being 1, that's what that means. And then I times hydrogen to the power of 3. You can see that? So PH2Q. So that is what this forward order thing is saying. And in the reverse order, K prime times F prime basis equals to K prime times, so you can see it's reverse order in H2O and methanol, so it's PH2O times PCH3OH. So if you look at your kinetics, it will probably look something like this. So there'll be some forward order and then some reverse order. So this is what it's talking about here. Then of course you'll have all these as well. Okay, so I'm going to copy and paste some of the things over, then I'm going to explain slowly. Okay, so I'm just going to copy it over because I don't want to explain it, you know, key everything from scratch. So it seems that we can't quite, you know, copy the whole thing over as easily. So I'm just going to copy it one at a time. Sorry. Yep. So we look at the 1.4 E minus 9, then I'm going to put a minus 75400. Then CO2 is 0, hydrogen is 1, and the rest is 0. So we're just looking at hydrogen in this case. Okay, so we're going to take a look at the, it's going to be 0 in everything except hydrogen. So we're just going to look for hydrogen. I'm just going to key in 1. I'm going to save. You can imagine this is actually quite tedious, but you know, that's the kind of thing you have to do if you're going to do it in a nice, slow, non-careless way. Of course, there are probably better ways to do it. I'm just demonstrating you the slow method so don't get overwhelmed so quickly yet. Okay, so the second one, 4.4 E minus 9. 4.4 E minus 9 is 1 in CO2 and 0 for everything else. So that's 1 in CO2. I'm going to press save. So I'm controlling S, control S-ing a lot. And 1.1 E minus 10. So these are the bottoms. So they come in the Arrhenius form as well. So A1, E1, that's what it's saying here. A and E. So let's move on. Minus 293. Minus 293. Okay, I'm going to press save. Minus 293, and then you'll be first order in methanol. So we'll have to look for methanol. 1. So copy this over. And basically it's 75400. And it's first order in water. So that's one is in water. Water. And finally the last one. So it's minus 75400. So it's first order in carbon monoxide. So let's go look at that carbon monoxide. So that's why we added in carbon monoxide previously. And the last thing we must note is this denominator exponent, which is 3. And what is this denominator exponent? Let me show you. Okay, so you see this Langmuir-Hinshelwood thing here. The denominator is a square. You can see the square here, and that means that the denominator exponent in that case is 2, because the denominator is squared. If it's cubed at the bottom, then the denominator exponent is 3. If it's to the power 4, then the denominator exponent is 4. So yeah, that's all I have. We have just for this video, it's like 25 minutes already, and we are just barely keying in the first reaction kinetics. So I mean, keying in the kinetics is quite easy compared to, let's say, validating it. Now that will be a much tougher challenge, but we'll stop here for now because it's already been 25 minutes. So probably see you in the next video. Thanks for watching, guys. Hope you find this helpful. Hey, bye bye.